A while ago I made an LM1875 amplifier, and listening to it, it doesn't seem to have as good a low frequency response with the same speakers as a LM1876 amplifier that I made, which I use mostly on the TV actually. And when I put the case on it recently, I realized that I'd never tested it. So in this video I want to show some tests that I need to do to make sure it is actually working correctly. So I want to check it with a better power supply. I want to check to make sure that I've made the input circuits correct, because they act as a high pass filter with a cutoff frequency about, I think, 2 or 3 hertz. I want to make sure the amplifier is not oscillating. I want to actually measure the frequency response, and I want to see how the amplifiers behave when I load them to as high a load as I can with a load that I made. So this is the load. I made it the other evening out of bits that I had lying around. So there's just a metal bracket, some bolts, and just a metal plate, and the heatsink and 4 10 watt 4.7 ohm power resistors. So there's 2 pairs. So I get about just under 10 ohms. Should dissipate 20 watts, possibly more with the heatsink. So now I just want to make sure that when I put 20 watts into it that it doesn't get too hot. It shouldn't, but I just want to confirm that it's okay and that my soldering was good. So I connected the load up to my power supply and organised so there's about 20 watts into each pair of resistors, and just check the temperatures. So I've left it on for a while, and the heatsink gets up to 70 something degrees. The resistors get up to 80 max. I don't think my thermometer works that well, but it's hot enough to hurt. But no smoke's coming off, so that's good. This is turned off. I have to wait now for it to cool down. The first thing I want to do is confirm that I've implemented this correctly, because this is a high pass filter. I'm always there drawn showing just the capacitor and another resistor. I'm not sure what effect this resistor has, but I calculated though that 1 meg in parallel with 22k is 21,526 ohms, so it doesn't make much difference. So if I calculate the cutoff frequency with 21, which I've already done, 21,526 ohms and 2.2 microfarads, it's 3.36 hertz, which is good. Or it's 22k, 3.2. So that means that filter should work fine. So it shouldn't. I would have thought that wouldn't affect the bass response too much. So if I now measure across the input, I expect to get 1 meg. Although when I first measured this, I was surprised because something I didn't expect happens. But it's because the capacitor's there. Although I don't understand why it goes so high, but then it goes down and then creeps up to 1 meg as the capacitor charges. Because yeah, there shouldn't yeah, when it's charged, there's no current flowing through the capacitor, no DC. So yeah, about 1 meg. So at least that part of the circuit's correct. So just try to test the other one. So it does roughly the same thing. It creeps up. So at least that is correct. Now I'm going back and doing a rough check of the topology of that input filter. I'm pretty sure it's correct because I don't think they would work. So I but it's just a second check to make sure there's no silly thing going on. So there's 22k. So I checked the 22k resistor on the filter. It's a bit fiddly. Probably should take them out, but I don't want to. I don't want it to disturb it. And I'm lazy. It gets a bit fit. Should have taken the other panel off, I think. The other grill off the other side. Then I think I'm going to change the continuity. Just checking. Yeah. I mean, I don't want it to be working by accident, but I think it's okay. It's such a simple thing, but I mean, I've made mistakes. It's very easy to make mistakes. And something, out of focus. The effort, I've been trying to get a better method of doing the photography, but I need a robot. A robot arm would be good. Or something that reads my voice, that understands my voice and says, put the camera there. See, I'm just doing another visual inspection as well of them, just to make sure there's. But again, I'm pretty sure it's correct. I'm thinking that I should replace this with a circuit board though, because making a bit of noise. I'll just be happier with it. Although I'm not sure if this actually is working correctly, then there's not necessarily much point. Rough. So all those bits of aluminium are all grounded. Got ground straps. So I've connected it to power, and I'm giving it a signal from the oscilloscope signal generator. So at the moment it's plus or minus 20 volts. It's about 4 or 5 watts. Seems to vary a bit. I don't understand that. This test actually raises more questions than it answers. So nothing gets hot, although this is pretty low wattage, I think. But the problem I'm seeing is I'm inputting a 20 Hertz square wave and I'm getting out that the green is the output, and I've read that that wave shape means that there's a low frequency cut. I'm really not sure. So I got 11.1 volts peak to peak out and 300 millivolts in. There's a bit of noise on the input, but that may be just the probes. So I'm not clear about what this means. It changes as you go up, so that when you raise the frequency, the top of the output gets better and better. I'm wondering what's happening, because when I 620 hertz, it's getting much flatter. I don't know where the noise is picking up noise from, probably something in this room. If I use a sine wave, what I find, I have to make sure the probes. So I'm using, what I find with a sine wave is at 20 hertz it's 6 volts peak to peak, and at 20 kilohertz it's 6.6. So I don't actually understand what that means. It seems to me to mean that that the frequency response is fairly flat. I need to do some more research about how to calculate what the number of decibels that means that's down. The thing will output like half a megahertz. So now I'm leaving the input amplitude constant and changing base. So now it's 20 kilohertz, and it's 6.6. I'm not sure if I 6.6 volts. So this image of the square wave where it's got that diagonal droop worried me. At first I thought it was because I'd used in power resistors, which are wire round, which act like inductors, but I tried with a 47k resistor and made a difference. And I'm just confirming here that both channels are the same. But I did some searching and found that an article on a website which I'll put in the description, which talks about characterizing quickly an amplifier with square waves, and that points to this article, which shows that this is what it looks like when you're capacitively coupling the input, even when the coupling filter is a lower frequency than the square wave. So I'm just measuring here with the cursors the minimum peak to peak and the maximum peak to peak, and you pump that into that formula, and you can calculate the cutoff frequency of the filter. So I don't understand how this can happen, because it seems as if the shape of the square waves is affected by frequencies lower than the main frequency of the square wave, which is 100 hertz. But apparently that's how it works. So I organized the oscilloscope. So this is 100 hertz. It's a 100 hertz square wave, and I just organized the screen so I've got the maximum accuracy, and so I'm just using again the cursors. I'm still having focus problems, and so the minimum is 2.406 volts peak to peak, and the max is whatever it is. And I think I confirm here that when the cursors are at the same place it's 0, so I'm looking at the right thing. So delta y. It's a bit fiddly. Yeah. So just organising myself. So we're getting 3 point whatever that is, 3.35. I can't believe how difficult it is to photograph the. Okay, so I'm just confirming that it goes to 0. I can't believe how difficult it is to photograph the screen. So now I'm going to take those numbers and calculate the cutoff frequency of the input filter. So the formula is FCL equals V max peak to peak minus V min peak to peak times F divided by V max peak to peak times pi. And so max is 3.331 and min is 2.406. So if I calculate that, 3.331 minus 2.406 times 100 hertz divided by 3.331 times 8.8 8.82 hertz. So when you calculate the filter input filter, which is 1 meg, is a 1 meg in parallel with a 22k, and then there's the capacitor is 2.2 microfarads. That's about 3 hertz. So there must be other resistance, I guess, affecting that. But what that's hopefully means is there isn't a problem with the bass response. So, and measuring the frequency response just by measuring the output of the amplifier with the same input from 20 hertz and then 20 kilohertz. So that, I think that was at 20 hertz it was 6 volts peak to peak, and at 20 kilohertz it was 6.6. So I think that the amplifier is working reasonably. At least I hope so. So I will, but not in this video, actually take a lot of points and then plot it and figure out more accurately the frequency response. So doing this video has forced me to look a bit more deeply into how these things work, although it does demonstrate that I'm not that familiar with analog electronics. But I've learned something, so I hope someone found it a little bit interesting, and thanks for watching.